New York's in love with Big Wilson, and it's very likely you will be too. Hear him every morning, Monday through Friday at 6:60.
In just a moment, we'll take a look into the sky and try to figure out if anyone is looking back.
Journey into Nature, a special series of programs produced by WNBC in cooperation with the American Museum of Natural History, an institution dedicated to the search for knowledge in the fields of natural science. Within the many exhibit halls of the museum, you will find accurate representations of what man has learned of himself and the world that surrounds him. Journey into Nature visits many of the exhibits, talks with the staff members and research scientists in order to capture in sound the wealth of knowledge on display, to bring you the excitement of learning, to explore the wonders of the world. Here now is your host, Tex Antoine.
Thank you. After man crossed the threshold of space and set his sights on worlds beyond his own, a question that had plagued him for centuries began to take on larger dimensions. Could life, as he knew it, exist on any of the stars or planets? Scientists had already pretty much discounted the existence of life on the moon, and studies of Mars seemed to demonstrate the same thing. Yet the question persisted. A rocket shot past Venus sent back information indicating that the planet's surface was too hot to sustain life as we know it. But speculation continues as scientists probe meteorites and extract substances that may be the remains of animal or vegetable life. We'll talk more about these substances and generally about the possibility of life in outer space this morning with Dr. Brian H. Mason, chairman of the Department of Mineralogy at the American Museum of Natural History. Dr. Mason, just what are these fascinating substances scientists are finding in meteorites?
Well, they've been finding black, sooty material, and also by extracting these meteorites with solvents, they have been getting out quite complicated organic compounds, hydrocarbons particularly, but other compounds as well.
Well, is this a new discovery in the research into meteorites?
We should perhaps say it's a rediscovery. The fact that some meteorites contain organic compounds has been known for over 100 years. But it wasn't until about 1950 that this very interesting fact was, so to say, rediscovered, and people started to wonder just what is this significance. Actually, meteorites as scientific objects have been studied since about 1800. And in 1806, the first one of these so-called carbonaceous chondrites fell at a village, Alais, in France. This meteorite was sent to the most famous chemist of the day, Berzelius in Sweden, for analysis. Berzelius had been analyzing meteorites before. When he received the Alais meteorite, he said, "I don't think this is a meteorite. It doesn't look like any meteorite I've ever seen before. It looks just like a piece of hardened clay." He wrote back to the Frenchman who sent it to him and said, "You have sent me a piece of soil from the ground where the meteorite fell. This is not the meteorite." But then Berzelius explained that he looked at it more closely and found it wasn't just an ordinary piece of soil. He found that it did have certain characteristics which indicated that it was a meteorite, in spite of the fact that it was so different from any other meteorite he'd ever seen. And he found that he could extract organic compounds out of it by heating it gently. These organic compounds would sublimate out of it, and he was able to collect them. And of course, in 1834, when he did this work, chemistry, and especially organic chemistry, was very much in its absolute beginnings. And with the techniques and the procedures available to Berzelius, he was not able to actually identify the compounds. But he showed quite clearly that this particular meteorite, the Alais meteorite, contained organic compounds, and Berzelius himself speculated. He said, does this indicate the presence of life where this meteorite came from?
Oh.
So
well,
it's a rediscovery, as I say, rather than a totally new discovery, but it's interesting to see how discoveries are made, and because science has not developed to the necessary degree at the time, it falls into limbo and has to be rediscovered at a later time.
Well, are these mysterious compounds found in all meteorites?
No, only in this very small group known as the carbonaceous chondrites. Now, out of about 1,500 known meteorites, only 20 are carbonaceous chondrites. It is also true that even the more common types of meteorites usually contain trace amounts of carbon and organic compounds, but it's only the carbonaceous chondrites which contain them in appreciable quantities. By appreciable, I mean more than 1%. Carbonaceous chondrites contain between 1 and 5% of organic material, along with silicates and other compounds.
Well, I can understand the French scientist's confusion. Dr. Mason was kind enough to bring down a sample of a carbonaceous chondrite in a little pill box, and it really looks like portions of my backyard. Very, very hard, dry, and surprisingly soft. I notice it crumbles with just gentle pressure.
It crumbles very, very easily.
Then it would be difficult for the average amateur to even identify one of these,
yes,
if it were in his backyard.
This is a very grave problem. I think actually that carbonaceous chondrites fall more frequently than this number of 20 indicates. I think there are many cases when we hear about a great fireball, a great streak of light and smoke in the sky, which is indicative of a falling meteorite, and yet we never recover any material. And I suspect that some at least of these are carbonaceous chondrites, because if it falls into a plowed field, that it would take a remarkably sensitive person to recognize this as against a piece of clay.
I was going to say that being so destructible, yes, it would permeate the ground like buckshot.
And of course, as soon as it rains, these things contain soluble compounds. As soon as it rains on them, they simply disintegrate. Whereas other meteorites, stones and irons, they will last for centuries, thousands of years. But a carbonaceous chondrite, if you don't get it when it falls, you will never get it, because the first rain will destroy it.
Isn't that strange? To endure the unfathomed trip through space only to be destroyed so immediately here on our surface. Well, from this crumbly little matter I have here before me, how do scientists go about extracting organic compounds?
The standard technique today is to use a sequence of solvents. Usually you start off perhaps with water, and then you extract it with alcohol, and then perhaps with petroleum ether, carbon tetrachloride. Each of these solvents will extract a certain type of the organic compounds. And then you can evaporate your solvent, and you are left with this residue, which maybe look like a wax or look like a resin or an oily material. It should be emphasized, however, this only gets out a minor quantity of the total amount of organic matter there. Most of the organic matter is not soluble. Most of the organic matter is a black, sooty material. You see that meteorite, how black it is. This is a very, very fine-grained soot. It's not graphite because it's not crystalline. The little work that's been done on it indicates it also is a very complex organic material, something like a bitumen or an asphalt or something of this sort.
Yeah, this reminds me of just a piece of old-fashioned coke.
Yes.
About the same coloration and texture, too.
Or a piece of tire off the road.
That's true. Yes. It could be that. Well, does the fact that a scientist finally draw from a meteorite like this organic compounds, does that mean that he has necessarily found the remains of some form of life?
No, this is an important distinction which we must make here, is that we talk about organic compounds, and there is a natural tendency to think organic compound means organism. This, of course, is how the name originated. Originally, it was thought that these compounds were all formed through living matter. We now know it, or we've known it since Wöhler back in 1828 made urea from ammonium cyanate, that you can make the typical organic compounds by non-biological means. And the chemist synthesizes enormous quantities of compounds nowadays, say from carbon monoxide and hydrogen. You can make these synthetic petroleums.
Yes.
So that the mere fact that we find organic compounds in these meteorites is not proof that they were produced by organisms.
It could have been then at least assumed that it is possible that through its travel through space and adjustment of chemicals surrounding it and heat, that it in turn synthesized these organic
we
compounds?
know, for example, that the atmosphere of Jupiter contains methane and ammonia and water, so that under the right circumstances we have the conditions in outer space where quite complicated organic compounds can be made simply by radiation on gases.
Oh. Well, then, let's again take a hypothesis. Suppose a scientist discovered an organic compound and can prove it was biological in origin and not synthesized someplace in outer space. Would even this be absolute proof of life someplace else beyond the Earth?
I would think it would be an extremely strong indication, but I would like to throw a question back at you or our audience. How do you prove that an organic compound is biological in origin?
I'll leave that to you.
There is one possibility that has been suggested, that life as we know it on the Earth is characterized by organic compounds which have what is known as optical activity, which means that if you make a solution, put them into a solution, you put them in a beam of polarized light, that the plane of the polarization of the light is rotated. Now, it would be most interesting if the organic compounds that we find in meteorites showed this activity, but so far no such activity has been detected. So this is perhaps a piece of negative evidence or a piece of evidence against the biological origin of these compounds. On the other hand, perhaps by more sensitive equipment or by getting more material, we may eventually find optical activity in these compounds, and that would be an extremely strong, I would think evidence for a biological origin. But so far, this has not been.
Well, have any of the organic compounds found turned out to be substances completely different from anything we know here on Earth?
No, so far they look very much like the material that we find, for example, in sediments from the ocean floor, where you have organic matter falling in and being buried in it. In fact, this is the analogy which the people who've been extracting these compounds have made, that they compare what we may call the spectrum of compounds, the various types of compounds and their abundances, with the spectrum of compounds which they can extract, say, out of a petroleum or out of a marine sediment, and they find quite close similarities, for example, between the hydrocarbons out of the meteorites and the hydrocarbons they can extract out of marine sediments. And that was the basis on which it was originally suggested that these organic compounds in the meteorites were the remains of some extraterrestrial life.
Well, Dr. Mason, there are several more fascinating questions I'd like to ask, but perhaps right now we can take just a moment to pause for a message from the American Museum of Natural History.
One of the goals of the American Museum of Natural History is to further science education among children. The museum is therefore pleased to announce publication of a new magazine, Nature and Science, designed for young people in the 9 to 14-year-old age group. The magazine will be useful both to individual boys and girls who want to subscribe at home and to school classes as part of the science curriculum. Teachers will find practical and imaginative suggestions for using the magazine in classroom and fieldwork in a special teacher's supplement of each issue. The new magazine, Nature and Science, will be prepared under the guidance of a national board of editors made up of elementary school teachers and scientists particularly concerned with new methods of teaching science to children. Regular publication will begin in September. For further information, write to Nature and Science Magazine, Department A, the American Museum of Natural History, New York 24, New York.
Thank you. This morning our subject is the possibility of life in outer space. And I'm happy to have with us Dr. Brian H. Mason, chairman of the Department of Mineralogy at the American Museum of Natural History. Dr. Mason, you mentioned earlier that many of the compounds found in the meteorites could be synthesized someplace in space, because we can synthesize pretty much the same things here. But if I recall correctly, I remember reading someplace that they think they have found fossilized, organized groups in these meteorites that might have some other indication.
Yes, that's true. About 2 years ago, Dr. Klaus and Dr. Nagy announced the discovery of so-called organized elements in these carbonaceous chondrites. When you examine a carbonaceous chondrite under high magnification, you do see numerous regular objects. And they felt that some of these objects resembled algae and suggested that they might be fossil algae from outer space. This has caused, of course, a great deal of discussion amongst the biologists and the geologists and everyone who is interested in meteorites, because if this is true, if they are fossil organisms, then, of course, we do have life in outer space, in the place where the meteorites came from.
Mm-hmm.
Well, there are various explanations for these organized elements. The explanation that we've just mentioned, that they are extraterrestrial fossils, is only one of them. One explanation that has been put forward is that these are actually terrestrial contaminants. These are things that have got into the meteorites since they came into our atmosphere. Now, this is a possibility because, as you have seen, these meteorites are very, very porous. They come into our atmosphere from the vacuum of outer space, so immediately they start to breathe in material.
That would be true.
They will breathe in air, and the air contains spores and pollen grains. They land on the ground. They lie on the ground for some time before they're collected. They're passed often through many hands before they finally reach the apparent security of a museum. But even a museum is full of exotic organisms from our own collections, so that there is clearly a great possibility of contamination. And some of the most spectacular of the organized elements, I am sure, are pollen grains or other such objects, but not all of them can probably be explained this way. But then you have other possibilities too, that they might be inorganic or organic crystals. Professor Morrison at Cornell University made a very nice analogy when he suggested maybe these are carbonaceous snowflakes. You know,
yes.
You know the intricate nature of a snowflake? The mere fact that you have an intricate, regular form is not necessarily an indication that it was an organism. You can make very complicated things, as I say. Snowflakes are very regular, very complicated, and yet are certainly not biological. So we have these three possibilities, that the organized elements are extraterrestrial fossils, or that they are terrestrial contaminants, or that they are, shall we say, sports of non-biological origin.
Dr. Mason, you mentioned a moment ago that scientists have not found organic compounds in meteorites which differed from those here on Earth. Has anything ever been found in meteorites that is completely different from the substances we know?
No, essentially meteorites are made up of the same sort of material as we find on the Earth. The Earth is probably made of material rather like the meteorites. The meteorites may be the material from which the solar system was formed, and in which case naturally we'd expect the Earth in its bulk to be rather like the bulk of meteorites, and this is a pretty good analogy, it seems. So far we have found nothing in meteorites which is exotic in terms of what we already know on the Earth.
Well, I can see that there are rapidly developing two schools of thoughts in this field. So would you go so far as to say that from what we now know of the materials extracted from meteorites, that we have absolutely no evidence of life in outer space?
I think that would be going a little too far, being a little too categorical. There are these two schools of thought, both backed by very sound scientists. One, that these organic compounds are the residue from biological life, one that they are non-biological. And I would certainly not say that we have absolutely no evidence of life in outer space. We have also the statistical belief that stars with systems of planets are rather common throughout the universe. And just statistically speaking, we would expect that somewhere in outer space there is a planet with some sort of life on it.
Mm-hmm.
But so far the meteorites have not proved this.
And actually, I guess in considering outer space, the meteorites that come to land on our own surface would be coming from a rather limited area of that outer space, leaving much still unexplored.
Exactly, that we don't even know precisely where these meteorites are coming from. It would help us a great deal if we could find out more about their passage before they came to the Earth.
Well, are there any other things, however, that we might speculate on from what has been taken from meteorites, besides perhaps life as we know it in outer space? Is it opening up new vistas or understanding of that spatial area?
Oh, a great deal. I think, if anything, this interest in the organic material in the carbonaceous chondrites tends to overshadow the great importance of research on meteorites generally. That a meteorite is a body which contains within it the history of at least 5 billion years, and in its chemical composition, its content of radiogenic and cosmogenic isotopes, all this history is there if we can learn to read it. And that is what the chemists and the physicists are working on intensively, because we can find the record of events which happened even before the Earth was formed inside the meteorites in terms of their chemistry, chemical and physical properties. And if we can decipher this story, it's a very complicated story and requires very intricate types of research, but nevertheless we are pushing back the time scale and what happened in the universe even before the solar system and the Earth existed by the study of meteorites.
Well, Dr. Mason, I'm afraid a lot of people may be disappointed by our discussion this morning. What were their expectations of Martians and little green hairy people up there looking down at us? But there certainly has been an interesting facet to the conversation of the scientist always leaving open that one vague possibility out there by saying definitely that we have no proof that there is absolutely no life out there. So for the dreamer and the looker into the heavens, he can continue to look with one raised eyebrow anyhow. We want to thank very much Dr. Brian H. Mason, chairman of the Department of Mineralogy at the American Museum of Natural History. This is Tex Antoine inviting you to join us again next Sunday morning at 11:05 here on WNBC, where we'll be waiting again to take you on another interesting journey into nature.
Journey into Nature has been a special program produced by WNBC in cooperation with the American Museum of Natural History. Join us again next week as we explore the museum, seeking out the natural wonders of our world. Journey into Nature is produced by Gary Stradling. Your host, Tex Antoine. This is Fred Collins. This program was pre-recorded and heard around the world through the facilities of the Voice of America and the Armed Forces Radio Service.
The preceding program was pre-recorded.